continuing from the first part of this video lecture, where we have seen already the motivation for a theorem, a general theorem that allows us to establish existence of measures. We have seen a type of measure which is very bad because it is finitely additive, but it doesn't have proper additive properties which include being countably additive. And now we go to discuss a property, a very mild property that we can require from a measure that is already enough to exclude this type of problem of being only finitely additive and not possible to extend to a countably additive measure. And see that this is enough. This is the CARATHÉODORY'S extension theorem. This is enough so that a measure specified on an algebra can be extended to a sigma algebra. And we see then the outer measures which are at the core of the proof of CARATHÉODORY'S extension theorem. So let's start with the definition of measures and the statement of CARATHÉODORY'S extension theorem. A pre-measure definition: if we have a sample space and an algebra of sets, of subsets of this sample space, pre-measure is the following. It is a finitely additive measure that we have already defined in the first part of this video lecture. Finitely additive measure is a measure satisfying these two conditions. And a finitely additive measure, we'll call it a pre-measure if moreover it satisfies one very mild condition, let me say that, which is asking it to be sigma additive. But sigma additive in a very precise sense, and the sense is the following. For every sequence of disjoint sets AN whose union happens to be in A, so this is a requirement that you make only in case the union of these sets is in A. If it's not in A, you don't require anything, because the measure is not even defined there in the first place. Okay? The measure is defined only for sets which are in A. Then, in that case only, when their union is in A, we require that the measure of their union is the sum of their measures. And the CARATHÉODORY'S extension theorem, it says the following: if we have an algebra on a sample space, an algebra of subsets, and we have a pre-measure on this measurable space, then this pre-measure can be extended to a measure on sigma algebra generated by A, which means we can define a new function, which by abuse I'm also denoting by the same letter mu, because it extends mu, in the sense that now we can this new mu, it goes from sigma of A to the non-negative extended numbers, whereas this mu, it was going only from A to the set of non-negative extended numbers. And when we say extend, it means that, of course, for sets A which are in this algebra, calligraphic A, these two measures that I'm denoting both by mu, they are the same. And this is in fact the only reason why I can denote them by the same letter in the first place. And moreover, if the extension is sigma finite, or if one of the extensions is sigma finite, then it is unique. Before discussing how we can use the CARATHÉODORY'S extension theorem, let's give an idea of how it is proved, and it's proved through the concept of outer measures. Outer measures, like finitely additive measures, are not measures. That's a little problem with the terminology here, but that's the established terminology. Let's take a deep breath. Here comes the definition of the outer measure. Okay? We're going to define the outer measure as follows. We have a pre-measure on an algebra of subsets of a sample space, and then we define the outer measure, which I denote by mu star, and the outer measure is defined for any subset, for every subset of the sample space. And it's defined as follows. Take a subset, E, of the sample space omega. And now we're going to consider the collection of sequences of sets in this algebra A that cover my set E. A picture would be the following. This is my set E. It looks like this, and I'm going to cover it with countably many sets of my algebra like this. Okay, so these are, each one of these is a set which is in my algebra of sets that was given, because the theorem assumes that the definition assumes an algebra is given and a pre-measure on that algebra is given, and here I have countably many sets from the algebra. There can be infinitely many of them, but countable. So this defines the family that I denote DE here. So this is a family of sequences of elements of the algebra. Then the outer measure, mu star, is defined as the infimum of the measures of all these collections that can cover the set like this. So we try to cover the set with the least amount of waste, and in the limit, or as we take the infimum, this defines as a number for us. We call that number the outer measure of the set E. And the idea behind this definition is that it is able to exclude pathological sets such as the Vitali set that we saw in the first week of this module. And to exclude pathological sets, we do the following. We consider sets E such that the E and the complement of E, when they intersect any other set, their outer measures add. And this is somehow saying this would be the measure of E seen from outside, and this would be the measure of E seen from inside, if we can make sense of that. And for sets E that satisfy this relation, we call them mu star measurable. And we define the collection of all sets that are mu star measurable. We define it by F star, and it's no coincidence that we're using calligraphic F here. This is exactly the lemma of CARATHÉODORY, is that this is a sigma algebra. This will come in a couple of slides. Here are the main properties of outer measures that we'll use. It is not so hard to prove them, but we will omit the proof. The outer measure satisfies the following. For sets A which are already in the algebra, the outer measure coincides with the pre-measure. If a set A is contained in B, then the outer measure of A is at most equal to the outer measure of B. And finally, the outer measure is countably sub-additive. If we have a sequence of sets, it doesn't matter if they are disjoint or not, the outer measure computed at their union is bounded from above by the sum of the outer measure of each of these sets. And using those properties, it is possible to prove, but we omitted in this module, the CARATHÉODORY'S lemma, which says the class F star of mu measurable sets is a sigma algebra. It contains A, and if we restrict the outer measure to evaluate it only on sets of this family here, the family of measurable sets, then it is a measure. So it is not only sigma sub-additive, it is sigma additive. This is a very complicated proof that we omit, just like the pi lambda theorem, whose proof we have also omitted. The proof of CARATHÉODORY extension theorem is not so complicated once we already have the properties of outer measure that we accept without proof and CARATHÉODORY'S lemma from the previous slide. You can see the proof in the lecture notes.